Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. Do you find your mind troubled with the stresses of modern life, especially when the lights are out and you're trying to get a restful night? Does your spinning mind keep you awake? Follow my voice down the path towards a good night's rest. Listen to me tell a story that will keep your mind from wandering to your daytime problems. The ones you can't solve right now and will be easier to solve well rested. Listen to my voice and allow yourself to drift, following the twists and turns of the story, but slowly letting go and drifting into sleep. Let my voice wash over you at a comfortable volume and allow yourself to be distracted from the stresses and worries that play on your mind. Whether you need help falling asleep or going back to sleep in the middle of the night, you can trust me to keep you company and help you to wake up tomorrow in a rested state. You may need to try out Sleepy Time Tales for a few nights to get used to the slightly strange idea, but I believe it will be well worth your while. I'm here to work with you, to create a safe space, a cocoon in which you can curl up and allow nature to take its course. So settle down, relax, and allow yourself to get lost in my telling of tonight's story. And just a quick note before we get to tonight's reading. I'd like to remind you that Sleepy Time Tales is a listener-supported podcast. I can only keep it going, paying for the services and tools I use, and justify the time that I use on it, thanks to the generosity of listeners like you. So if you find Sleepy Time Tales useful, if it helps you to get a restful night, and you'd like to keep it going out to thousands of your fellow insomniacs, please consider supporting on the Patreon at patreon.com/sleepytimetales. If monthly support is a big ask, you can also just throw a little something in the tip jar on the website at sleepytimetales.net. And if you'd like to help out the show without having to do so financially, you can just tell people about it. If you know someone struggling to sleep, let them know where to find Sleepy Time Tales and let it go from there. Have a fun note on tonight's reading. We're returning to Astronomy, the Science of the Heavenly Bodies by David P. Todd. And in the book is reference to spiral nebulae, which they didn't know at the time yet was galaxies. And recently it was the 100th anniversary of Edwin Hubble discovering that what they called spiral nebulae were actually whole other galaxies outside of the one that which we lived in. So I think it's pretty cool timing. Also, there's a bit of advice on how to look at the sun towards the end of the reading, if you make it that far. Please don't take most of that advice, especially the stuff about using smoked glass to look at the sun. If you want to do that, there's much safer modern ways to do so. Anyway, that's enough of that. Let's get to learning about our solar system. We return once again to Astronomy, the Science of the Heavenly Bodies by David P. Todd. The policy of undertaking the interpretations of celestial phenomena of laboratory experiments, an important element in the initial organization of Mount Wilson, has certainly been justified by its results. Indeed, the development of many of the chief solar investigations would have been impossible without the aid of special laboratory studies, going hand in hand with the astronomical observations. So indispensable are such researches, and so great is the promise of their extension, that the time has now come for advancing the laboratory work from an accessory feature to full equality with the major factors in the work of the observatory. Accordingly, a new instrument now under installation is an extremely powerful electromagnet, designed by Anderson for the extension of researches on the Zeeman effect and for other related investigations. Within the large and uniform field of this magnet, which is built in the form of a solenoid, a special electric furnace designed for this purpose by King is used for the study of the inverse Zeeman effect at various angles with the lines of force. This will provide the means of interpreting certain remarkable anomalies in the magnetic phenomena of sunspots. The 100-inch telescope is now in regular use. All the tests so far applied show that it greatly surpasses the 60-inch telescope in every class of work. For many months, most of the observations and photographs have been made with the Cassegrain combination of mirrors, giving an equivalent focal length of 134 feet and involving 3 reflections of light. The 100-inch telescope is found to give nearly 2.8 times as much light as the 60-inch telescope, and therefore extends the scope of the instrument to all the stars an entire magnitude fainter. This is a very important gain for research on the faint globular clusters, as well as the small and faint spiral and planetary nebulae, providing a much larger scale for these objects, and sufficient light at the same time. Photographs of the Moon and many other less critical tests have been made with very satisfactory results. Those of the Moon appear to be decidedly superior in definition to any previously taken with other instruments. Another investigation is of great importance in the light of recent advances in theoretical dynamics. Darwin, in his fundamental researches on the dynamics of rotating masses, dealt with incompressible matter, which assumes the well-known pear-shaped figure, and may ultimately separate into 2 bodies. Roche, on the other hand, discussed the evolution of a highly compressible mass, which finally acquires a lens-shaped form and ejects matter at its periphery. Both of these are extreme cases. Jeans has recently dealt with intermediate cases, such are actually encountered in stars and nebulae. He finds that when the density is less than about 1/4 that of water, a lens-shaped figure will be produced with sharp edges, as depicted by Roche. Matter thrown off at opposite points on the periphery, under the influence of small tidal forces from neighboring masses, may take the form of 2 symmetric filaments, though it is not yet entirely clear how these may attain the characteristic configuration of spiral nebulae. The preliminary results of von Manen indicate motion outward along the arms, in harmony with Jean's views. Jean further discusses the evolution of the arms, which will break up into nuclei of the order of mass of the Sun, if they are sufficiently massive, but will diffuse away if their gravitational attraction is small. The mass of our solar system is apparently not great enough, according to Jeans, to account for its formation in this way. As is apparent, these investigations lead to conclusions very different from those derived by Chamberlain and Moulton from the planetesimal hypothesis. This is a critical study of spiral nebulae for which the 100-inch telescope is, of all instruments in existence, the best suited. The spectra of the spirals must be studied, as well as the motions of the matter composing the arms. Their parallaxes, too, must be ascertained. A photographic campaign including spiral nebulae of various types will settle the question of internal motions. The large scale of the spiral nebulae at the principal focus of the Hooker telescope, and the experience gained in the measurement of nebular nuclei for parallax determination, will help greatly in this research. A multiple slit spectrograph, already applied at Mount Wilson, will be employed, not only on spiral nebulae whose plane is directed towards us, but also on those whose plane lies at an angle sufficient to permit both components of motion to be measured by the 2 methods. In dealing with problems of structure and motion in the galactic system, the 100-inch telescope offers special advantages because of its fast light-gathering power. Studies of radial velocities of the stars have hitherto been necessarily confined to the brighter stars, for the most part even to those visible to the naked eye. While some of these are very distant, most of the stars whose radial velocities are known belong to a very limited group, perhaps constituting a distinct cluster of which the Sun is a member, but in any event of insignificant proportions when contrasted with the galaxy. Current spectrographic work with the 60-inch telescope includes stars of the 8th magnitude and some even fainter. But while the 60-inch has enabled Adams to measure the distances of many remote stars by his new spectroscopic method, and to double the known extent, so far as spectroscopic evidence is concerned, of the star streams of Kapteyn, a much greater advance into space is necessary to find out the community of motion among the stars comprising the galactic system. The Hooker telescope will enable us to determine accurate radial velocities to stars of the 11th magnitude, which doubtless truly represent the galaxy. In order to secure a maximum return within a reasonable period of time, the stars in the selected areas of Kapteyn will be given the preference, because of the vast amount of work already done, relating to their positions, proper motions, and visual and photographic magnitudes. Such consideration as spectral type, the known directions of star streaming, and the position of the chosen regions with reference to the plane of the galaxy are given adequate weight. And it is of fundamental importance that the method of spectroscopic parallaxes will permit dwarf stars to be distinguished from stars that are in the giant class, but rendered faint by their much greater distance. In addition to these problems, the stellar spectrograms will provide rich material for study of relationship between stellar mass and speed, and the nature of giant stars and dwarf stars. Shapley's recent studies of globular clusters have indicated the significance of these objects in both evolutional and structural problems, and the possibility of determining the parallaxes by a number of independent methods is of prime importance, both in its bearing on the structure of the universe and because it permits a host of apparent magnitudes to be at once transformed into absolute magnitudes. Here, the advantage of the Hooker telescope is twofold. At its 130-foot focus, the increased scale of the crowded clusters makes it possible to select separate stars for spectrum photography, which could not be done with the 60-inch, where the images were commingled. And the great gain in light is such that the spectra of stars to the 14th magnitude have been photographed in less than an hour. Faint globular clusters then will comprise a large part of the early program with the 100-inch telescope. The faintest possible stars in them must be detected, and their magnitudes and colors measured. Spectral types must be determined, and the radial velocities of individual stars and of clusters as a whole. Spectroscopic evidence of possible axial rotation of globular clusters must be searched for, and the method of spectroscopic parallaxes, as well as other methods, must be applied to ascertaining the distances of these clusters. The possibility of dealing with many problems relating to the distribution and evolution of the faintest stars depends upon the establishment of photographic and photovisual magnitude scales. Below the 12th magnitude, the only existing scale of standard visual or photovisual magnitudes is the Mount Wilson sequence, already extended by Sears to magnitude 17.5 with the 60-inch telescope. Extension of this scale to even fainter magnitudes, and its application to the faintest stars within its range, is an important task for this great telescope, as it will doubtless bring within range hundreds of millions of stars that are beyond the reach of the 60-inch. The giants among them will form for us the outer boundary of the galactic system, while the dwarfs will be of almost equal interest from the evolutional standpoint. The photometric program of the 100-inch, then, will deal with such questions as the condensation of the fainter stars toward the galactic plane, the color of the most distant stars, and the final settlement of the long inquiry regarding the possible absorption of light in space. Another research of exceptional promise will be undertaken, which is of great importance in a general study of stellar evolution. and that is the determination of the spectral energy curves of stars of various classes, for the purpose of measuring their surface temperatures. Very few of the nebulae are found to be variable, and the peculiarities need investigation. Also, special problems of variable stars and temporary stars and the spectra of the components of close double stars, which are beyond the power of all other instruments to photograph. Such a program of research conveys an excellent idea of many of the great problems that are under investigation by astronomers today, and gives some notion of the instrumental means requisite in executing comprehensive plans of this character. It will not escape notice that the climax of instrumental development attained at Mount Wilson has only been made possible by an unbroken chain of progress, link by link, each antecedent link being necessary to the successful forging of its following one. In very large part, and certainly indispensable to these instrumental advances, has the art of working in glass and metals been the mainstay of research. As we review the history of astronomical progress, from Galileo's time to our own, the consummate genius of the artisan and his deft handiwork compel our admiration almost equally with the keen intelligence of the astronomer, who uses these powerful engines of his own devising to wrest the secrets of nature from the heavens. Chapter 24. Our Solar System. Now let us go upward in imagination, far, far beyond the tops of the highest mountains, beyond the moon and sun, and outward in space, until we reach a point in the northern heavens millions and millions of miles away, directly above and equally distant from all points in the ecliptic, or path in which our Earth travels yearly round the sun. Then we should have the sort of comprehensive view of the solar system which is necessary if we are to visualize as a whole the working of the vast machine, and the motions, sizes, and distances of all the bodies that comprise it. Of such stupendous mechanism our Earth is part. Or in lieu of this, let us attempt to get in mind a picture of the solar system by means of Sir William Herschel's apt illustration. Choose any well-leveled field. On it place a globe 2 feet in diameter. This will represent the sun. Mercury will be represented by a grain of mustard seed on the circumference of a circle 164 feet in diameter for its orbit. Venus, a pea, on a circle of 284 feet in diameter. The Earth, also a pea, on a circle of 450 feet. Mars, a rather larger pin's head, on a circle of 654 feet. The asteroids, grains of sand in orbits of 1,000 to 1,200 feet. Jupiter, a moderate-sized orange in a circle of nearly half a mile across. Saturn, a small orange on a circle of 4/5 of a mile. Uranus, a full-sized cherry or small plum upon the circumference of a circle more than a mile and a half. And finally Neptune, a good-sized plum on a circle of about 2 miles and a half in diameter. To imitate the motions of the planets in the above-mentioned orbits, Mercury must describe its own diameter in 41 seconds, Earth in 4 minutes 14 seconds, the Earth in 7 minutes, Mars in 4 minutes 48 seconds, Jupiter in 2 minutes 56 seconds, Saturn in 3 minutes 13 seconds, Uranus in 2 minutes 16 seconds, and Neptune in 3 minutes 30 seconds. Now let us look earthward from our imaginary station near the north pole of the ecliptic. All these planetary bodies would be seen to be traveling eastward around the sun, that is, in a counterclockwise direction, or contrary to the motion of the hands of a timepiece. Their orbits or paths of motion are very nearly circular, and the sun is practically at the center of all of them, except Mercury and Mars, of Venus and Neptune. almost at the absolute center. The planes of all their orbits are very nearly the same as that of the ecliptic, or plane in which the Earth moves. These and many other resemblances and characteristics suggest a uniformity of origin, which comports with the idea of a family, and so the whole is spoken of as the solar system, or the Sun and his family of planets. In addition to the 9 bodies already specified, the solar system comprises a great variety of other and lesser bodies. No less than 26 moons or satellites tributary to the planets, and traveling around them in various periods, as the moon does round our Earth. Then between the orbits of Mars and Jupiter are many thousands of asteroids, so-called, or minor planets. About 1,000 of them have actually been discovered, and their paths accurately calculated. And at all sorts of angles with the planetary orbits are the paths of hundreds of comets, delicate filmy bodies of a wholly different constitution from the planets, and which now and then blaze forth in the sky, their tails appearing much like the beam of a searchlight, and compelling for time the attention of everybody. Connected with the comets, and doubtless originally parts of them, are uncounted millions of meteors, which for the time become a part of the solar system, the minute masses being attracted to the planets upon which they fall, those hitting the Earth being visible to us as familiar shooting stars. We next follow the path of astronomy through the solar system, beginning with the Sun itself and proceeding outward through his family of planets, now much more numerous and vastly more extended than it was to the ancient world, or indeed to within a century and a half of our own day. Chapter 25. The Sun and Observing It. As Lord of Day, King of the heavens, mankind in the ancient world adored the Sun. By their researches into the epoch of the Assyrians, Hittites, Phoenicians, and other early peoples now passed from Earth, archaeologists have unearthed many monuments that evidence the veneration in which the early peoples who inhabited Egypt and Asia Minor many thousand years ago held the Sun. A striking example is found in the architecture of early Egyptian temples, on the lintels of which are carved representations of the winged globe or the winged solar disk, and there is a bare possibility that the wings of the globe were suggested by type of the solar corona, as glimpsed by the ancients. Little knew they about the distance and size of the Sun, but the effects of his light and heat upon all vegetal and animal life were obvious to them. Doubtless this formed the basis for their worship of the Sun. Occasional huge spots must have been visible to the naked eye, and the Sun's corona was seen at rare intervals. Plutarch and Philostratus describe it very much as we see it today. How completely dependent mankind is upon the Sun and its powerful radiations, only the science of the present day can tell us. By means of the Sun's heat, the forests of early geologic ages were enabled to wrest carbon from the atmosphere and store it in forms later converted by nature's chemistry into peat and coal. Through processes but imperfectly understood, the varying forms of vegetable life are empowered to conserve, from air and soil, nitrogen and other substances suitable for and essential to the life maintenance of animal creatures. Breezes that bring rain and purify the air, the energy of water held under storage in stream and dam and fall, trade winds facilitating commerce between the continents, oceanic currents modifying coastal climates, the violence of tornado, typhoon, and waterspout, together with other manifestations of natural forces, all can be traced back to their origin in the tremendous heating power of the solar rays. In everything material, the Sun is our constant and bountiful benefactor. If his light and heat were withdrawn, practically every form of human activity on this planet would come to an early end. How far away is the Sun? What is the size of the Sun? These are questions that astronomers of the present day can answer with accuracy. So closely do they know the Sun's distance that it is employed as their yardstick of the sky, or unit of celestial measurement. Many methods have been utilized in ascertaining the distance of the Sun, and the remarkable agreement among them all is very extraordinary. Some of them depend upon pure geometry, and the basic measure of which we make from the Earth is not the distance of the Sun directly, but we find out how far away Venus is during a transit of Venus, for example, or how far away Mars is, or some of the asteroids are at their closer oppositions. Then it is possible to calculate how far away the Sun is, because one measurement of distance in the solar system affords us the scale on which the whole structure is built. But perhaps the simplest method of getting the Sun's distance is by the velocity of light, 186,300 miles a second. From eclipses of Jupiter's moons, we know that light takes 8 minutes, 20 seconds to pass from Sun to Earth, so that the Sun's distance is a simple product of the two, or 93 millions of miles. Once this fundamental unit is established, we have a firm basis on which to build up our knowledge of the distances, the sizes, and motions of the heavenly bodies, especially those that comprise the solar system. We can at once ascertain the size of the Sun, which we do by measuring the angle which it fills, that is, the Sun's apparent diameter. Finding this to be something over half a degree in arc, the processes of elementary trigonometry tell us that the Sun's globe is 865,000 miles in diameter. For nearly a century, this has been accurately measured with the greatest care, and diameters taken in every direction are found to be equal and invariably the same. So we conclude that the Sun is a perfect sphere, and so far as our instruments can inform us, its actual diameter is not subject to appreciable change. The vastness of the Sun's volume commands our attention. As his diameter is 110 times that of Earth, his mere size or volume is 110 times 110 times 110, or 1,300,000 times that of the Earth, because the volumes of spheres are in proportion as the cubes of their diameters. If the materials that comprise the Sun were as heavy as those that make up the Earth, it would take 1,300,000 Earths to weigh as much as the Sun does. But by a method which we need not detail here, the Sun's actual weight or mass is found to be only 300,000, or more nearly 330,000, times greater than the Earth's. So we must infer that bulk for bulk, the component materials of the Sun are about 1/4 lighter than those of the Earth. That is, about 1 1/2 times as dense as water. To look at this in another way, it is known that a body falling freely towards the Earth from outer space would acquire a speed of 7 miles a second, whereas if it were to fall toward the Sun instead, the velocity would be 383 miles a second on reaching its surface. If all the other bodies of the solar system, that is, the Earth and Moon, all the planets and their satellites, the comets and all, were to be fused together in a single globe, it would weigh only 1/750th as much as the Sun does. At the surface, however, the disproportion of gravity is not so great, because of the Sun's vast size. It is only about 28 times greater on the Sun than on the Earth. And instead of a body falling 16 feet the first second there, it would fall 444 feet there. Pendulums of clocks on the Sun would swing 5 times for every tick here, and an athlete's running jump would be scaled down to 3 inches. Let us next inquire into the amount of the Sun's light and heat, and the enormous high pressure of a body whose heat is so intense, even at the vast distance at which we are from it. The intensity of its brightness is such that we have no artificial source of light that we can readily compare it with. In the sky, the next object in brightness is the full moon, but that gives less than 0.5 millionth part as much light as the sun. The standard candle used in physics gives so little light in comparison that we have to use an enormous number to express the quantity of light that the sun gives. A sperm candle burning 120 grains hourly is the standard, and if we compare this with the sun when overhead, and allow for the light absorbed by the atmosphere, we get the number 1575, with 24 ciphers following it, to express the candle power of the sun's light. If we interpose the intense calcium light or an electric arc light between the eyes and the sun, those artificial sources will look like black spots on the disk. Indeed, the sun is nearly 4 times brighter than the crater, or the brightest part of the electric arc. The late Professor Langley at a steelworks in Pennsylvania once compared direct sunlight with a dazzling stream of molten metal from a Bessemer converter. But bright as it was, sunlight was found to be 5,000 times brighter. Equally enormous is the heat of the sun. Our intensest sources of artificial heat do not exceed 4,000 degrees Fahrenheit. But the temperature at the sun's surface is probably not less than 16,000 degrees Fahrenheit. 1 square meter of its surface radiates enough heat to generate 100,000 horsepower continuously. At our vast distance of 93 millions of miles, the sun's heat received by the Earth is still powerful enough to melt annually a layer of ice on the Earth more than 100 feet in thickness. If the solar heat that strikes the deck of a tropical steamship could be fully optimized in propelling it, the speed would reach at least 10 knots. Many attempts have been made in tropical and subtropical climates to utilize the sun's heat directly for power. And Ericsson in Sweden, Mouchant in France, and Schumann in Egypt have built successful and efficient solar engines. Necessary intermission of their power at night, as well as on cloudy days, will preclude their industrial introduction until present fuels have advanced very greatly in cost. All regions of the sun's disk radiate heat uniformly, and the sun's own atmosphere absorbs so much that we should receive 1.7 times more heat if it were removed. So far as is known, solar light and heat are radiated equally in all directions, so that only a very minute fraction of the total amount ever reaches the Earth. That is, 1/220,000 millionth part of the whole. Indeed, all the planets and other bodies of the solar system together receive only 1/100 millionth part. The vast remainder is, so far as we know, effectively wasted. It is transformed, but what becomes of it, and whether it ever reappears in any other form, we cannot say. How is this inconceivably vast output of energy maintained, practically invariable through the centuries? Many theories have been advanced, but only one has received nearly universal assent: that of secular contraction of the sun's huge mass upon itself. Shrinkage means evolution of heat, and it is found by calculation that if the sun were to contract its diameter by shrinking only 250 feet per year, the entire output of solar heat might be thus accounted for. So distant is the sun, and so slow this rate of contraction, that centuries must elapse before we could verify the theory by actual measurements. Meanwhile, the progress of physical research on the structure and elemental properties of matter has brought to light the existence of highly active internal forces, which are doubtless intimately concerned in the enormous output of radiant energy, though the mechanism of its maintenance is as yet known only in part. Abbott, from many years' observations of the solar constant at Washington, on Mount Wilson, and in Algeria, finds certainly evidence of fluctuation in the solar heat received by the Earth. It cannot be a local phenomenon due to disturbances in our atmosphere, but must originate in causes entirely extraneous to the Earth. Interposition of meteoric dust might conceivably account for it, but there is sufficient evidence to show that the changes must be attributed to the Sun itself. The Sun, then, is a variable star, and it has not only a period connected with the periodicity of the sunspots, but also an irregular, non-periodic variation during a cycle of a week or 10 days, though sometimes longer, and occasioning irregular fluctuations of 2 to 10% of the total radiation. Radiation is found to increase with the spottedness. Attempts have been made on the basis of the contraction theory to find out the past history of the Sun and to predict its future. Probably 20 to 50 millions of years in the past represents the life of the Sun, much as it is at present. And if solar radiation in the future is maintained sustainably as now, the Sun will have shrunk to 1/2 its present diameter in the next 5 million years. So far then as heat and light from the Sun are concerned, the Sun may continue to support life on the Earth not to exceed 10 million years in the future. But the Sun's own existence, independently of the orbs of the system dependent on it, might continue for indefinite millions of eons before it would ever become a cold, dead globe. Indeed, in the present state of science, we cannot be sure that it is destined to reach that condition within calculable time. A few words on observing the Sun, an object much neglected by amateurs. On account of the intense light, a very slight degree of optical power is sufficient. Indeed, a piece of window glass, smoked in a candle flame with uniform graduation from end to end, will be found worthwhile in a beginner's daily observation of the Sun. The Sun should be smoked densely enough at one end so that the sunlight as seen through it will not dazzle the eye on the clearest days. At the other end of the glass, the degree of smoke film should be not quite so dense, so that the Sun can be examined on hazy, foggy, or particularly cloudy days. An occasional naked eye spot will reward the patient observer. If a small spyglass, opera glass, or field glass is at hand, excellent views of the Sun may be had by mounting the glass so that it can be held steadily pointed on the Sun, and then viewing the disk by projection on a white card or sheet of paper. Care must be taken to get a good focus on the projected image, and then the faculae, or whitish spots, or mottling near the Sun's edge will usually be well seen. By moving the card farther away from the eyepiece, a larger disk may be obtained, in effect a higher degree of magnification. But care must be used not to increase it too much. Keep direct sunlight outside the tube from falling on the card where the image is being examined. This is conveniently done by cutting a large hole, the size of the brass cell of the object glass, through a sheet of corrugated straw board and slipping this on over the cell. In this way, the spots on the Sun can be examined with ease and safety to the eye. For large instruments, a special type of eyepiece is provided, known as a helioscope, which disposes of the intense heat rays that are harmful to the eye. Frequent examination of the eyepiece should be made, and the eyepiece cooled if necessary. That part of the Sun's surface under observation is known as the photosphere, that is, the part which radiates light. If the atmosphere admits the use of high magnifying powers, the structure of the photosphere will be found more and more interesting the higher the power employed. It is an irregularly mottled surface showing a species of rice grain structure under fairly high magnification. These grains are grouped irregularly and are about 500 miles across. Under fine conditions of vision, they may be subdivided into granules. The faculae, or white spots, are sometimes elevations above the general solar level. They have occasionally been seen projecting outside the limb or edge of the disk. And that's the end of the chapter, so I'm going to call it there. First off, if you ever do want to look at the Sun, don't take the advice in this book, especially the smoked glass stuff. This is over 100 years old, so we now know better. But if you'd like to pick up where I'm leaving off, you can, as always, find the original on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night, and sweet dreams.